So, remember from last time when we talked about negation, the negation of P not P is true when P is false and false otherwise? And we had this truth table. We even talked about not P. So, let's do more. Let's go to two variables. Two. RJ the Scholar presents Math-0400 Introduction to Mathematics, Chapter 1, Logic, Section 1.2, Logical Connectives of two or more propositions. Okay, so we've got our first operation on the board, and it's conjunction. This is for our concept of and. So, A and B. So, the conjunction of P and Q, it's pronounced P and Q, is true if both P and Q are true, and false otherwise. And we have our trusty, handy-dandy truth table. Do you love the truth tables now? I hope you do. You probably don't. But you'll learn to say, oh, those are so nice. I wish we could go back to just doing truth tables. But no, we must move farther and further in mathematics. So, P and Q. Okay. If both P and Q are true, then P and Q is true. So, we put a T here, because they're both true. And there are 4 inputs here, because there are 4 possible combinations of P and Q. True, 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 false, false, true, false, false. And if there were 3 variables, we'd use 8 rows, because there would be 8 possible combinations. And you have to list each and every one of them. I'm listing them true, 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 false, false, true, false, false, because it's kind of a counting down in binary. Why is it counting down in binary? Well, because this is 2. This, no. This is 3, this is 2, this is 1, and this is 0 in binary. So, counting down from 7 in binary would be this, and then you'd go 111, 110, 101, 100, then you do 011, 010, 001, and 000. This is 7, 6, 5, 4, 3, 2, 1, 0 in binary. It's we'll be able to learn how to count in binary if you want to know more about this counting down system in binary of representing the truth tables, but it doesn't matter for this course. You'll be able to continue the generalized pattern. It's basically, if you have, the initial one is 1, 0. Then you copy it, and then you do, for every 1, then you do that. And you copy that, and you do 0, 1, 1, 0, 1, 0, 0, 0, 1, and 0, 0, 0. So it's basically, this is the differences for each variable, and that's how it works. Might not be too enlightening, but when we actually do it in practice, you'll understand. So, okay. it's false otherwise. It tells us that. After our brief digression, we're ready to go back to the truth table. So P and Q, remember what we did before? It's true if both P and Q are true. But when one of them is false, it's false. And if one of them is false here, it's false. And if both of them are false, I'm sorry to say it, but it's also false. So sad. So very sad. But alas, there's only one. And this is what we would expect from an and. So now we're going to treat this as our definition. I have this here. I wrote it down so I didn't forget it. But we have to treat this as a definition. We're going to treat these truth tables as definitions. I'm going to explain to you what they should understandably mean, but I'm not going to spell it out for you. I'm not going to say right here. You're going to just rely on the truth tables. Because, honestly, those are better. They just list every input and every output. So I'll tell you an idea you can get in your head for what it means, but it's more useful to think of it as a sort of true. It's just it's like an addition, but there's only 4 ways it can go. It's like a single digit addition if there was only 2 types of digit, 0 and 1. So, for example, let P be, this symbol means let it be. Basically, we're just assigning a value. So let P be cows are animals, which is a true statement, and Q be cows are pigs, a false statement. And then P and Q, which is cows are animals and pigs, is a false statement because true and false is a false. Just remember that. It's just simple. If it's not simple, please put it in my comments down below so I can expand upon it in a companion video. But I think it's simple. The concept of and is so ingrained in our English language. This is the and of the English language. Basically, if A and B is true, A and B is true. But if we see cows are animals, but cows are pigs, that's the same as saying cows are animals and pigs. It's only a word difference. But just means we're not expecting it. It's a slight semantic difference in the English language that makes no difference in logic. And that's why we don't give it a difference. So yeah, that is and. And we're gonna move on to disjunction. Okay, so let's talk about the disjunction. Disjunction, fine. I'm not gonna do that. So the discussion of disjunction, never mind. The disjunction of P and Q. That's what we're talking about. Denoted P or Q. That's what it's read. P or Q. This symbol, this V, it's or. Has truth table, and this is what we describe here. So it has truth table. If both of them are true, P or Q is true. If one of them is true, P or Q is true. If one of them is true here, if Q is true and P is false, P or Q is true. Only if they're both false is P or Q false. So we can aptly describe it as true if one of the inputs is true. And I'm defining it by its truth table here, not by words. Because that's essentially what we're still going to get. But we need to get comfortable with using truth tables and defining things using truth tables. Because that's basically all we have. We want to make sure we're founding it on basic things, not our English language. The truth table matters more than the English language description of it. It tells us how it acts in all cases, and it tells us what it means. So for example, we have our same propositions as before for the conjunction. But P is cows are animals and Q is cows are pigs. One's true, one's false. And the statement P or Q, cows are animals or pigs, is a true statement, different from our and. And I wanna take the time to stress the difference between not and or, but between or and exclusive or. There is a thing called exclusive or, and I will not talk about it because it's not really the scope of this propositional logic, nor logic that we need to do, because exclusive or can be modeled with just these operations. And in fact, each and every one of these can be, there's only actually one operation that you need. And it's the negation, it's NAND. It's NAND. You only need NAND, which is not and. So if you have A not and A, that's not. If you have not of not A, no, if you have not of, if you have not A, NAND, not B, you have or, A or B. If you have not A, NAND B, we have A and B. We have all of those operations. We can get them. And you know, you're wondering how I got them. Well, it's a funny thing called De Morgan's Law. But that's for a later time. That's for next lecture, actually. So, if you want to know more about De Morgan's Law and everything like that, watch the next lecture. So, there's a difference between OR and XOR. And what is XOR? XOR is called exclusive OR. And why do they call it exclusive OR? Because it is actually different from OR in one way. It is basically P or Q and not P and Q. It means that you can only have one of P or Q true. It's like you can have your pudding or your ice cream. It's not a choice of you can have both. That's what the exclusive OR is. Now, I want you to say to people, when they say you can have pudding or ice cream with your entree, you say yes. And when they respond, which of them do you want? You say, I told you, both. But you can only have one. You said I could have pudding or ice cream. You didn't say pudding or ice cream. Ha 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 ha. You can make them, you can get kicked out if you try that. I haven't done that myself. I have not gotten kicked out of a restaurant, though I do imagine they would. So maybe don't do it. Or maybe do it at a place you never want to go to. That's probably where you want to do it. But I digress. So that's the disjunction operation. See you in the next one, which will be implication. Oh! It changed again. Oh, it didn't change this time. The magic of editing. Okay, let's talk about implication and how that relates to you. The implication P implies Q has the truth table. Well, it's not filled out yet, so let's fill it out. So I'm filling it out. I want to see what you think of it. It's kind of weird, isn't it? Like, okay, I get and or. But what's this? There's only one false, and that's when P is true and Q is false. What does that even mean? So, let me give you the idea behind the implication. And I want you to understand this. The implication is true if P being true means that Q is true. Doesn't work the other way around. Doesn't mean that if Q is true, that P is true. That's a logical fallacy. It just means that P is a necessary condition. As P is a sufficient condition for Q. And vice versa. Q is a necessary condition for P. Means P can only be true if Q is true. If that's not how it happens, then P implies Q is false. It's kind of like a promise a politician makes. For example, oh my goodness, we got an example. A politician says, if I am elected, I will solve climate change. That's kind of a P implies Q, where the P is I am elected, and the Q is I will solve climate change. So if he's elected, and he solves climate change, he's kept his promise. If he's elected and he hasn't, well, he hasn't kept his promise. That's logic for you. Making politicians pay. Yeah. It's not fun. Okay. But what if P is false? I can't believe it. P being false? No. Well, yeah. If P is false, then P implies Q is true. Huh? You may say, but you remember, the implication is true if P being true means that Q is true. P isn't true. So Q can be whatever it wants. P doesn't care. It's still true. This is what we call a vacuous condition. If the politician isn't elected, he doesn't have to do anything. He could solve climate change if he wants to, but he doesn't have to. His campaign promise doesn't obligate him to do anything. Though he probably should solve climate change because he's... This is not a video about climate change. This is a video about logic. Okay, let's do more logic. This is the implication. Over. Next thing, whatever I do, is the biconditional. So, okay, guys, let's talk about the biconditional. It's the last one, so we don't have to worry about any more logical connectives after this. We'll have all of them in our tool belt. We'll have them all in our tool belt. So the biconditional P if and only if Q has truth table this. So it's only true when P and Q have the same truth value. So if P and Q are true, P if and only if Q is true. If they have a different truth value, the P if and only if Q is false. But if they have the same truth value, even if it's false, false if and only if false is true. And as a quick example, Jimmy is a dingleberry if and only if Jimmy is a dongledoo, means that being a dingleberry means you're a dongledoo. And honestly, it's probably right. So when I start calling people dingleberries, just replace it with dongledoos. I made those words up. But I wanted you to understand that this kind of defines an equivalence concept with logic. So, yeah, that's it. That's it for our second lecture. If you liked it, well, like, comment, and subscribe, and ring the bell, because YouTube, I just keep saying it. Ring the bell, ring the bell. But you need to. Come on. You want to do it. I know you want to do it. So do it. Anyway, have a great day. Have lots of fun. Learn lots. And most of all, remember to keep learning. Art of the Scholar, done with Lecture 2.